All right, section 3.9. So this is abstract stuff. But if and so this is it's a weird kind of thing, I think. On the one hand, if you're doing very few differential equations ever, this is probably all overkill. If you're doing more differential equations than that, the whole perspective through linear algebra, I think, ultimately simplifies what's going on here. But time will tell what you think of it. In any case, it's very mathy stuff. So we're going to bring it all back to differential equations here over these next two sections. And I've been trying to keep connecting it with derivatives and integrals. The idea is these things that we're doing anyway, derivatives, functions, integrals, these are all just examples of something more general. And by viewing it through this more general lens, we can see certain patterns or ideas that will help us construct solutions to differential equations. So a linear differential operator, sorry, an nth order linear differential operator is just a bunch of derivatives. So remember these capital D's are ddt's. This is the nth derivative. This is n minus 1th derivative, all the way down to the first derivative. These coefficients are functions. They could be constants, like 4. They could be sine of t. They could be t squared. They could be anything. All right. Right. So yeah, the d's are derivatives. D cubed is d, or this. So the idea is that any linear differential equation can be expressed as some L acting on a function giving you some result. And so we're going to get there very shortly. All right. So before we can use this sort of stuff in chapter 4 to solve differential equations, we have to see how differential equations are just linear differential operators applied to functions. So we've been doing some of this multiplication. And if you have a d plus a constant times a d plus a constant, these things will commute. And so let's do this out. D plus 1 times d minus 2. All right, we're going to end up with 4 terms. D commutes with constants, meaning if I had a function f here, you could just pull the constant out. This is really tricky. Sometimes folks see this and they say, okay, well, this is 0. The derivative of a constant is 0, right? Yes, but we're not taking the derivative of anything yet, right? There's no function here. There's no function here. This is all something that's applied to a function, which we will in a second. All right. So we end up with this d squared minus d minus 2. It's definitely not clear to you why we're multiplying these together to get this. So just hold on for 10 seconds. If I give this operator a function, f, what's f? I don't know. It's just a function. Then what would I get? Well, I'd have 2 derivatives, so f double prime, minus 1 derivative, f prime, minus 2 times the function. That's what you get when you take this operator and you apply it to a function. All I need is an equal sign and a 0, and I have a homogeneous differential equation of order 2. So what we're doing is we're working our way towards differential equations so that we can work backwards. And it's not going to be clear at the moment why working backwards to these pieces would be helpful, but it's going to be. And the reason it's going to be helpful is this. These little operators, d plus a, so d plus 1, d minus 2, these form little differential equations. D plus a applied to f equals 0. This is a differential equation. You've already solved this. This is the same as f prime plus af equals 0, which is the same as f prime equals minus af. This is that equation that I keep saying is one of the most important equations in differential equations. It's just exponential growth. Separate variables if you want, or recognize that only the exponential function has a derivative equal to itself times a constant. So we've done this a bazillion times. That's the answer to this type of question. And similarly for this one. What's going to happen is that when we start with a second order differential equation, we'll factor it and we'll solve little first order equations and get the answer for the second order equation from these parts. That's what we're going to do. So, for example, and again, we're not starting this quite yet. This is 4.1. But I want you to know that it's connected, that this material is connected. So if I had a differential equation like this, I can rewrite it. 2 derivatives, d squared. 3 times the derivative, 3d. 2, 2. There's an x, an x, and an x. I can pull that out to the right. And then what I have here is a linear operator. It's a combination of d's and constants. I can factor it, and it will turn out that the e to the minus t and the e to the minus 2t here will form the solutions. X will be expressed as the sum of 2 solutions to 2 first order equations. That's where we're going with this. Okay. We still need one more section to ground it, but that's why we're multiplying things and foiling and factoring. That's where we're going with this. All right. So broadly, a linear differential equation can be thought of as Lx equals f of t, where L is the linear differential operator, x is the unknown function, and f of t is the non-homogeneous term. Sometimes we can factor L and solve the equation this way. Sometimes we can't, that's supposed to be can't, because of commutation issues, and we'll deal with those in chapter 4. And even when we can't, this idea will help us construct new ways of dealing with it. So these ideas of thinking about differential equations as linear operators acting on vectors will be our conceptual framework for understanding most of chapter 4. Pause for practice.